Welcome to the DIY Honda Garage channel. This presentation covers DTC P16E3, indicating a battery sensor LIN communication error for the 2011 to 2016 Honda CRV. Understanding this specific diagnostic trouble code, DTC, is crucial as it pertains to communication failures between the Powertrain Control Module, PGM, and the battery sensor. The battery sensor plays a vital role in monitoring battery conditions and ensuring proper functioning of the vehicle's electrical system. It is generally located close to the battery and connects to various components, including the PCM and alternator via the LIN, Local Interconnect Network circuit. This diagnostic guide will delve into the causes, symptoms, and, importantly, the step-by-step troubleshooting procedures necessary to effectively resolve this issue. DTC P16E3 refers to a communication error with the battery sensor via the LIN bus. The battery sensor is responsible for monitoring the battery's voltage and state of charge, ensuring the vehicle's electrical system operates smoothly. This sensor effectively communicates data to the PCM, which processes this information to optimize engine performance and fuel efficiency. The battery sensor is typically found positioned close to the vehicle's battery itself, where it can accurately monitor its conditions. Communication failures in this context suggest issues may arise from wiring, connectors, or the sensor itself, which may lead to symptoms affecting vehicle performance. Several potential causes can lead to DTC P16E3 being triggered. One common issue is loose terminals at the battery sensor or other associated components. Loose connections compromise electrical integrity and can result in intermittent or complete failure of communication. Another potential cause is poor connections elsewhere in the circuit, particularly at the alternator and the PCM. These must be verified to ensure they maintain a robust connection. Lastly, a malfunctioning battery sensor itself could also be the root cause, leading to the communication error. Each of these causes requires thorough investigation to ensure effective troubleshooting and problem resolution. The symptoms manifesting from DTC P16E3 can range from mild to severe, affecting vehicle operation. One prominent symptom is the loss of critical battery data relayed to the PCM, which could impact fuel efficiency and overall engine performance. Drivers may also experience increased electrical issues, such as dimming lights or dashboard warnings, signaling a more significant problem within the electrical system. In some cases, as this communication error persists, the vehicle might exhibit decreased performance when starting or while driving, further necessitating immediate troubleshooting. Recognizing these symptoms early can help prevent more extensive damage and costly repairs. In the initial troubleshooting step, it's important to set the vehicle's ignition to the on I2 position to ensure all systems are activated for checks. Following this, the diagnostic tool known as HDS, Honda Diagnostic System, should be utilized to clear the DTC. This process allows the system to reset any stored error codes that may have been created. Once cleared, it's essential to wait for 10 seconds before checking again for any pending or confirmed DTCs using the HDS. If DTC P16E3 is indicated again, the issue is likely to be persistent, indicating that deeper investigation is required in the next steps. Step 2 involves another check for pending or confirmed DTCs using the HDS. By identifying if DTC P16E2 is present, technicians can narrow down the possible failure areas. If P16E2 is indicated, it suggests a LIN communication error related to the alternator. Should this DTC be confirmed, the troubleshooting path leads to the next step in the process outlined for P16E2. However, if P16E2 is not present, This implies the first issue might not be related to the alternator, but could still be linked to the battery sensor or other components in the LIN circuit. In this step, begin by turning the ignition switch to the lock 0 position, ensuring all electrical systems are powered down to prevent any accidental shorts or injury. The next action involves disconnecting the battery sensor's 2-pin connector to evaluate its integrity accurately. Following disconnection, the technician must check for continuity between designated test points, essentially between the battery sensor terminals and body ground. Continuity testing is vital to determine if the wiring has integrity and isn't shorted. If continuity exists, this indicates that the LIN communication circuit is operational, allowing the troubleshooting to proceed to the next steps. If continuity isn't found, this points towards other possible failure modalities, warranting further tests. In Step 4, utilize the HDS to jump the SCS line, the serial communication system, short, allowing the technician to further assess the integrity of the LIN circuit. While maintaining this condition, continuity must be checked between the battery sensor 2P connector terminal and body ground. This step requires systematic disconnection of various connectors, including the alternator and PCM connectors, one at a time. The intention is to observe if continuity is lost upon disconnecting any of these components, which would indicate the location of the fault in the LIN communication circuit. Should continuity remain while disconnecting these components, it likely confirms the LIN wire is intact, leading you towards necessary component replacement if loss of continuity occurs. For Step 5, the focus shifts back to the state of the battery sensor once again. First, reconnect the battery sensor 2P connector, ensuring all connections are secure. Afterward, disconnect the alternator's 1P connector to check the continuity of the LIN communication circuit. This time, you'll assess continuity between the alternator connector and body ground while ensuring proper testing conditions. By establishing a reliable connection, it becomes easier to verify whether there are any breaks or faults in the communication line, particularly concerning the battery sensor's LIN and the alternator. If continuity is present, it signals that the battery sensor itself is defective, prompting a replacement action to remedy the issue. Step 6 focuses on checking for open circuits in the LIN BAT sensor system. Here again, the SCS line should be jumped with the HDS to facilitate ongoing tests. Disconnect the battery sensor 2P connector alongside the PCM connector B49P. This prepares the circuit for continuity testing between the specified test points, specifically checking between the PCM connector and battery sensor 2P connector. Conducting this check in a deactivated state ensures jacketing and connections are not influencing results. Success in this step indicates that the LIN wire is functional, and further steps may involve updating the PCM software for optimal performance. Conversely, if there's no continuity, we head towards diagnosing an open circuit in the LIN wiring, necessitating repairs. In this 7th troubleshooting phase, the ignition must once again be turned to the lock position, prohibiting power to any electrical circuits. Following this, fuse number A14, comprising 10 ampere, located in the underhood fuse/relay box, should be checked meticulously for integrity. The status of the fuse is a vital aspect of the troubleshooting process. Should the fuse be found to be intact, it clears that aspect of electrical functioning. However, if the fuse is blown, it points to a possible short in the wiring, particularly in the +B horn wire connected to the circuit, necessitating further investigation and possible replacement. This basic fuse check can often identify a glaring fault in the system without extensive diagnostics. Step 8 demands a direct examination of the +B horn line functionality. Begin by disconnecting the battery sensor 2P connector, followed by measuring the voltage between test points to ascertain if battery voltage is present. This step can help identify open circuits affecting the system operation. A successful voltage measurement confirms the integrity of the +B horn wire, allowing troubleshooting to proceed. However, if there's no voltage detected, this suggests an open circuit in the wiring that must be repaired, ensuring communication restoration between the battery sensor and corresponding circuits. Such repairs can reaffirm the reliability of the electrical system. The final troubleshooting step revisits the integrity check for the LIN communication circuit involving the battery sensor. Jump the SCS line with the HDS to maintain effective communication while checking continuity. Disconnect the PCM connector B49P, ensuring to follow test protocol for accuracy. By measuring continuity between the battery sensor's LIN connection and the specified pin on the PCM connector, it becomes possible to analyze whether the communication pathway is intact. If continuity is confirmed, this indicates that the LIN communication line is functioning properly. You would then move to replace the battery sensor, a key component in this system. Alternatively, if continuity is absent, further checks for damaged wiring would be warranted, reaffirming the diligence required within this troubleshooting journey. Final repair verification is crucial after addressing the issues identified during troubleshooting. Begin by turning the ignition switch to the lock position and ensuring all connectors are securely reattached, including those for the battery sensor, alternator, and PCM. Once all connections are confirmed to be intact, switch the ignition back to the on-to position. Using the diagnostic tool HDS, reset the PCM to ensure it has the latest settings and configurations. The PCM idle learn procedure should then be performed to facilitate optimal engine performance. Finally, check for any pending or confirmed DTCs using HDS, ensuring that DTC P16E3 no longer appears. This verification step validates the resolution and stability of the system. Preventive maintenance is key in avoiding future occurrences of DTC P16E3. Frequent inspections of battery terminals and sensors can preemptively identify corrosion or loose connections. It's essential to ensure all components related to the battery sensor and LIN circuit maintain tight, clean connections to prevent communication errors. Reviewing the integrity of wires throughout the system is equally critical, as frays or exposure can lead to shorts or opens that trigger various DTCs. Establishing a habit of regular preventative checks will enhance the reliability of the electrical system while optimizing vehicle performance. Such diligence not only guards against surprises, but guarantees a more seamless motoring experience. In summary, DTC P16E3 signals a specific issue with the battery sensor LIN communication, necessitating detailed and methodical troubleshooting. Understanding the role of the battery sensor and its connections within the electrical network allows for efficient diagnosis and resolution. The steps outlined not only target this specific error, but create a framework for diagnosing similar issues in the future. Preventive maintenance practices play a significant role in enhancing vehicle reliability, reducing occurrences of such DTCs down the line. Being proactive rather than reactive can save time, money, and maintain safety on the road. This holistic approach ensures the longevity and performance of the Honda CRV's electrical system is safeguarded. Please like and subscribe to the channel. See you next time.